Hello, everybody. Welcome back for this very last lecture for this course on proofs and sets. There are many other cool topics that would be of interest, but well, there's only so much we can do within the course of a semester. So, well, let's get to it, shall we? Um, Um, okay. So last time we've done a number of things, right? So we've explained what numbers are, what it means for sets to have the same number of elements. We have proved some properties of natural numbers, especially we have proved the five axioms of Peano Dedekind arithmetic. And eventually, what we would want to do to have a full understanding of the foundations of the mathematics that we use in various courses would be to do the same thing for integers, rational numbers, real numbers, and who knows, perhaps even complex numbers. But that would be beyond what we can do within this last lecture. So I think the next important thing to do before we get there is to look at the operations that we can do on natural numbers, and we're going to look in particular to addition and multiplication and exponentiation. At the moment, those are undefined concepts. We haven't said exactly what an addition is, what a multiplication is, what an exponentiation is, right? So we're going to have to devise a strategy in order to figure out what those things are. Now, um, for some mathematical operations, not all of them, but for some of them, we can really understand those operations through a very simple sort of thought process, which is just about um, doing something simple, but doing it over and over and over again, right? And when that happens, we are really in luck because then we can define those operations on the basis of the set theory that we already have developed. And we don't need to add anything new, no new axiom, nothing else. We're just guaranteed that those operations exist and hopefully will show also that they have the properties that we expect them to have. And we don't need to introduce anything else except something called a recursive definition. Now, we don't need to introduce anything new to legitimize this approach, but it still takes a little bit of time to see how it's supposed to work and how why it's a legit thing to do within the confines of the approach to the foundations of arithmetic that we have developed. Okay, so our first step today is going to be to try to understand what's a recursive definition and how we can use that kind of definition to define the basic operations, addition, multiplication, and so on, that we do with natural numbers. Okay, so first I'm going to start with an example to give you an idea of what this simple repetitive process is. Suppose I asked you, what is 3 to the power 5 or 3 exponent 5? Uh, well, probably you've done some math before, so you would have an idea that 3 exponent 5 is just 3 times 3 times 3 times 3 times 3. So, right, you multiply 3 5 times. But if you break it down a little bit, instead of multiplying the 5 numbers all at once, you could look at it as a sequence of very simple steps where you just multiply two numbers, and that's going to be the basis for that process of recursive definition that we're going to look at. So 3 to the power, you start with exponent 0. 3 to the power 0 equals 1. Then you look at 3 exponent 1. Oh, that happens to be just 3, the base, multiplied by 3 to the power 0, the number that we have already calculated before, which is 1. So the result of 3 times 1 is just 3. Now, 3 to the 2 is again going to be understood in terms of multiplying 3 by the number that we just got before on the last line, which is 3 to the 1. So that gives us 3 times 3 equals 9. 3 to the power 3 is again going to be just 3 times the number that we got on the previous line, which is 3 to the 2. Right, so you see I'm decreasing my exponent one by one. This time I have 3 times 9 equals 7. 3 to the 4 is 3 times 3 to the 3, which is 81. 3 times the number I got on last line, and so on. So the idea of defining the value of a function in terms of the value that this function has for smaller arguments is the very essence of recursion that we're going to be trying to capitalize on to rigorously define those operations that we do with natural numbers. So I have a graphical way of depicting what is happening. And at first it might look a little bit intimidating, but fear not. So on the right-hand side, in that blue rectangle with rounded corners, I have depicted the ordered pairs that are part of that function, which takes a number and multiplies it by 3, because you saw that multiplication by 3 plays a very important part here. So at first, and here what we're trying to do is understand the function 3 to the power n. So the way it starts is we start with the value of that function, 3 to the power n, when n equals 0. That's 3 to the 0, number 1. So we use that as a seed value, which we use to figure out what pair in the graph of the function g we are going to start with. So we start with 1, and then we find what 3 times 1 is, which is the value, the second member of the pair. Now we're going to use that value of the function g, and we're going to look at what pair starts with that number. That's the pair 3, 9. Now, that's number 3, the first element here. We're going to assign it to f to the 1. Oh, that's 3 to the power 1. How cool, right? Then we're going to find the value of the function g when the input is 3, and we're going to multiply by 3. Again, we're going to go back to that pair whose first member is 3. Now that's going to be the input, or the number that we assign for f of 2, 3 to the power 2, which is 9. Then again, we're going to reapply the function g once more. That's going to give us 25, which is going to 27, sorry, which is going to correspond to 3 to the power 3. So you see how after we assign that seed value to f to the f of 0, all the other values that follow are obtained by successively applying the function g, so that we take the value, we apply the function g to it again, it gives us the next number, right? So that idea of having a seed value plus another function that gives us the other values of the function f is really this essential part of the recursion that we're trying to develop. So for n plus 1, or the successor of n, we're going to just apply the function g to the value of the function f, but not for n plus 1, for the one just before that, okay? So when we define a function recursively, we're going to have the pattern that you see at the bottom of the slide. F of 0, the function I'm trying to define, is going to be equal to a seed value. Now, for this whole process to work here, what I have is a function that I'm trying to define, f of n. But of course, I'm trying to define it in terms of that function, which is on the right-hand side here. And that function is assumed to be given because we have to know how we can successively apply that function. So it has to be already defined. And that's why I'm using the letter g for a function that is given, a function that is already known. So we try to define f in terms of g by recursion. So we start with the seed value, and then after that, the function as it applies to the successor of n, or n plus 1 as I've written here, is just applying the function g, the given function, to f, but with an argument 1 lower. Okay, so those two equations are the equations that we use in order to do a recursive definition. We say what's the value of f at 0, and then we say what is the value of a successor in terms of a given function applied to the function for the predecessor. That's the idea. And we're going to introduce 4 functions by recursion in what is coming. Of course, we could introduce many more, but 4 is going to be a good number given the time that we have. Okay, so I like that graphical way of thinking about recursion. It's pretty cool, I think. So the idea is that we start with a seed value in a given function and we define a new function based on that. And here, what this theorem does, this recursion theorem, it tells us that any function with a domain omega, the natural numbers, that is defined using those 2 equations, the recursive equations, that's always going to be a good definition, and that it uniquely defines a function. So that means our method works. So what is given is an element of S, a seed value, where S is any set. It doesn't have to be the natural number, any set whatsoever. G is a function that associates numbers of the set S to numbers, elements of the set S to elements of the set S. Could be anything, right? Really anything whatsoever. It doesn't have to be numbers. But the idea is that we start from a given function on a set S and a seed value, which is an element of the set S. And then we lay out those 2 equations, and that's going to define a unique functions from the natural number to that set S. So there's going to be a unique function that satisfies those 2 equations for any natural number n. So there's a proof of that theorem in the notes. If you're struggling a little bit with the proof, don't worry about it. It doesn't matter all that much. To me, what matters a lot more is that you understand how to utilize the recursion theorem in order to define those functions that we use to deal with numbers. So we're going to look at examples of how we can use that to define, the recursion theorem to define operations on natural numbers. So let's get started. So the first operation we want to define is addition, right? So coming back to that little graph, the function we want to define is the one on the left, the given function is the one on the right, and the seed value correspond to that first arrow that we have here. So for addition, the given function is just the successor function that we have studied in great detail in the previous lecture. So then, instead of introducing just one addition function, we're going to introduce, for each natural number, a different function, which is defined by recursion. We could do it differently, but it would be a little bit more tricky and difficult. So this is why I think it's simpler to do it that way. So for each natural number, we introduce a function a sub m. A stands for add, okay? Which take a number and sends it to another number. And intuitively, the idea is that it's going to take a number and send it to m plus that number. So the a function, a sub m function applied to 0 is going to give you m plus 0. And then the sum of m and the successor of n, so the sum of m and n plus 1, is going to be the sum of m and n plus 1. So the successor of the a function applied to m. So suppose we take a3, which is going to be thought of as the sum of 3 and some other number. So a3, by the first equation gives us the subscript, so it gives us 3. Now 3 plus 0 equals 3. Then 3 plus 1, 1 is the successor of 0, right? So A applied, A3 applied to the successor of 0 is the successor of A applied to 0, which we've already seen is 3, right? So it's the successor of 3, which is 4. Then what is the value of A3 applied to 2? Well, 2 is the successor of 1, you see, right? And we've already found the value of the function for 1, which is 4. So that's going to be the successor of 4, which is just 5. And you see how you can just keep going on and on and on and on. Now, for any number n, you would find the value of the function for that number just on the basis of the seed value by applying that pattern a finite number of time, which means basically a computer could do it. You don't need intuition, you don't need smarts, it's a purely mechanical process, okay? Now, since the function a sub m of n, as I said, corresponds to the sum of m plus n, we're going to introduce the notation m plus n by definition as being equal to to that function here, okay? Now, with that notational convention, then we can already show that addition has the properties that we expect, namely that it's associative. M plus n together plus k is the same as m plus n plus k together. You can change the order in which you do the addition and it doesn't change the result. And also, addition is commutative, so m plus n is the same as n plus m. So the way we prove those properties of addition, where addition has been defined recursively as we have shown, is going to be by induction, okay? Now, the first proof by induction is fairly easy, and the detailed proof is given in the notes. But the first thing we're going to want to do, because that one here, the second one, is a little bit trickier, and it's a good idea to start by proving those two theorems that are going to help us in proving that it is commutative, okay? So the first one is just to say for any number 0 plus n equals n. Duh, easy. Oh, we're going to prove it, right? And then we have for any numbers m and n, the successor of m, m plus 1, plus n equals s, the successor of m plus 1. So m plus 1 plus n equals the successor of m plus n. So the first one, I'm going to leave it as an exercise, and we're going to do the second one, and we're going to take our time, work it out with a Fitch diagram. So I've put it all together here, okay, as part of a Fitch diagram. So first of all, let me draw your attention on line 13. So here I've started with for all n in omega. But let's go back to what I wrote on last slide. It says for all m, which is the first quantifier, and then for all n. As you see, I've changed the order of the quantifiers, which is something we saw we can do in predicate logic. If we have two existential or two universal quantifiers, or three, right, you can change the order and it doesn't affect the result. All the sentences are logically equivalent. Now, the reason why we might want to do that is because sometimes it's easier to do induction on m than it is to do induction on n, okay? Or vice versa. Now, in this case, you can try it at home if you want to do your induction on m. It's tricky, a bit trickier than what we're going to do with n. So that's why I changed the order to keep our life a little bit simpler. You might be wondering, how do I know if I should change the order? I don't have a good answer. You just try and try, and you try all the combinations until you find one that works. So that's all there is to it. Okay, so here I put that quantifier in red to show you that I did change the order, but also the part in black that follows. Now that's a big expression, but look at this expression. N is a variable in that, right? So that whole element in black on line 13 is what we're going to use as the property phi n to do induction. So to do induction, we need the base case and the inductive step. I wrote the base case on line number 2, where you see I replaced n by 0, because that's the base case. And I put the inductive step that says that the property applies to n implies that the property applies to the successor of n. Okay? So let's look at the base case first. So what we try to do is we take an arbitrary object. Here I kept the letter m just to keep things simple. We try to show that the left-hand side of the equation must be equal to the right-hand side of the equation. So the left-hand side is the successor of m plus 0. Now, if we come back to our definition of addition, that tells us that that is equal to that function a sub sm, right? Remember the first term of the addition always goes as the subscript, and the second always goes as the argument. So I have a sub sm of 0. Now, if we look at our recursive definition, the addition function applied to 0 just returns the subscript, s of m. Okay? Then m, again, is equal to the function a sub m as it applies to 0. So here I've just replied m by something that it's equal to. So we get the successor of am0. And am0, just by definition of plus, is m plus 0. So I've shown that the left-hand side equals the right-hand side, which gives me my base case. Now, for the inductive step, we're going to do the same thing. We're going to try to, we assume the inductive hypothesis, and we try to reach our sub-goal here. Again, we're going to try to show that the left-hand side of the sub-goal equals the right-hand side of the sub-goal. If you look at the proof I've written in the notes, that's a proof in prose, and I've all written it on one line, but here I've broken it down to help you see how each of those steps works. In each of those lines, you're going to see that we have something equals a second thing, and that second thing is taken as the left-hand side of the next thing, and we're going to do one step each until we go from the left-hand side of line 4 to the right-hand side of line 10, and this equals this is just the sub-goal that we are trying to reach. Okay, so now you see we've replaced n by the successor of n in both cases. So we start with sm plus sn. Again, by the definition of plus, that means that we have the add function where the subscript is sm and the argument is sn. Now, when we see this, the argument is sn, that tells us that we should use the recursive clause, right? So on line 5, we have this left-hand side, which is the add function to some successor. So that means it's the successor of a sub sm of n. So we take that as the left-hand side of our next step. And then we apply our definition of plus. That's just sm plus n. And I've substituted the identicals here, as you see again. So now let's take that as my left-hand side. And that, in a way, on line 7 is the absolutely crucial step in that proof. Remember my inductive hypothesis? It's telling me that the successor of m plus n equals the successor of m plus n. So what is the argument of that first successor function here is substituted now using the inductive hypothesis. It's a substitution of identicals. Okay? So that's cool. Let's take that as our left-hand side. Now I'm using the recursive definition, but instead of going from left to right, I'm going from right to left. So the successor of m plus n is, oh no, sorry, I'm using the definition of plus on line 8, sorry, is just a sub m of n, okay? And now on line 9, I'm using my recursive definition the other way around. So I take that successor and I throw it inside here, okay? So that's equal to the successor of that term here, the sum of m and Sn. On line 10, I use the definition of plus. So that's where we start. So at first, as you see, we take something in terms of plus and we pack it in using the recursive definition until we can use our inductive step, and then we unpack it until we reach that last term here, which is again just true by definition of the recursive definition. So we went from the left-hand side of line 4 to the right-hand side of line 10, which gives us our last line here by universal introduction. So then we have our conditional proof, and then we do a universal introduction as well for n, and that gives us our inductive step, which gives us the result by induction. So that proof is very, very typical of how you would proceed in doing a proof by induction for a function that has been recursively defined. The other one that I left as an exercise here, 0 plus n equals n, is a sort of simpler version of what we're doing here, but it's going to work very much in the same way. So I encourage you to just work on that one first, because it might be the simplest one that you're going to have to do. Oh, by the way, later on, we're going to do recursive definitions of multiplication and exponents, and you're going to have to do proofs by induction for their property. It's also going to be useful to prove corollaries, and you might have to find them yourselves. But for example, for multiplications, you might have to show that 0 times n equals n for one of your corollary to simplify things. For the second one, it's going to be very similar as well. Okay, so that idea is going to be recurring as well. So here's what the multiplication is. And by the way, in the notes, there were a few typos here. Oh, I thought I changed it. The note said the given function g is the successor function, but then I write the addition. Of course, it should say the given function g is the the given function g is the addition function that we have just defined, okay? So that's the cool thing, right? So we start with the successor function, which we've studied, and then we define addition in terms of successor. Then we define multiplication in terms of addition. Then later on, we'll define exponentiation in terms of multiplication. So here's how we define P. P stands for product. Again, for each number m, we introduce a function P sub m from the natural numbers to the natural numbers. The first equation, P of m of 0 equals 0, just says m times 0 equals 0. But that's based on that recursive notation. And then m times the successor of m, that's m times n plus 1. Well, that should be, that will be defined as the sum of m and the product of m by n, which is just, using the plus notation, m plus m times n, the product mm. Okay? So if we use 3 again, we find that the product of 3 and 0 is 0. So the product of 3 and 1 is, using that term here, is, oh, I should have written it the other way around. It's 3 plus the product of 3 applied to 0. Why? Because 1 is the successor of 0. Now that term we've already calculated, that's 0. So the result is 3. Now P3 of 2, 2 is the successor of 1. So we get P3 of 1 plus 3 by the recursive definition. But we've already calculated P3 of 1, that's 3. So we get 3 plus 3, 6. Beautiful, right? So since P sub m of n is the product of m and n, we introduced that definition using the dot for the product. You could use the x as well, but we've used it for the Cartesian product, so that we don't overload the notation. We're going to use the dot for multiplication. Then we can show that there are some nice properties that follow. First is the distributive law. K times m plus n equals km plus kn. I think you learned that in grade school. They use sort of fireman analogy where K is a fireman that throws water on both him and I don't know what you guys have learned. But anyway, I hope you recognize that this is a good property about how addition and multiplication interact. The proof is going to be a proof by induction, and then yeah, you're going to do it by induction. It's not a super hard proof. I think, if I remember well from doing it, that doing an induction on n is the easiest, so you might want to change the order of those two quantifiers. But it's not a very hard one. It works very similar to the one we've looked at before. And also, multiplication is associative, which means it doesn't matter in which order you multiply the numbers. Again, that one is fairly straightforward. Here, I believe induction on k is the simplest one, if you try. And for addition, for multiplication being commutative, you might need to prove two earlier theorems, just like you would have to do to show that addition is commutative, just like we did. I've shown you two theorems to prove before. Here, that would be the same thing. So if you start doing your proof by induction for the commutativity of the product, and you're stuck at some point, you're like, I see that this is true, but how do I do that? Well, the idea is either start a second induction, an induction within an induction, or just prove it beforehand as a corollary that you are going to be using, like I suggested we do before. Okay, so I'm not going to prove those. I believe one of those or two of those are proved in the notes, so I didn't see the point of redoing it here. I just wanted to show you one of them as a Fitch diagram, and then you see how this is working. So let's turn to exponentiation. So the given function is just going to be the product that we've just defined. So we define exponentiation in terms of product, which itself was defined in terms of addition, which itself was defined in terms of successor. Right? So E sub m of 0 is intuitively thought to be m to the power 0. Right? So that's 1. And then m to the power n plus 1, m to the power successor n, should be just the product of m times e to the n. Right? So m to the n plus 1 is m times e to the n, and that's what that recursive definition is telling us here. Okay, so again, if you take e3, which means 3 to the power something, well, 3 to the power 0 is 1 by the seed value. 3 to the power of 1, well, 1 is the successor of 0, so that means that we get 3 times 3 to the 0. Oh, that's what's written here, right? 3 times 3 to the 0. Now we've already calculated 3 to the 0, it's 1. So 3 times 1 equals 3. 3 to the power 2. Well, 2 is the successor of 1. So that gives us 3 times 3 to the power 1, which we've already calculated. It's 3, right? So you see that you just keep multiplying by 3 like we did in our earlier picture that I have presented to you with colors. Okay. Now, since E sub m of n is thought of as the exponentiation of base m with exponent n, written this way, by definition, we write it that way. And then we get the properties that we would expect. B to the power m plus n just is b to the power m times b to the power n. Again, we prove that by induction. B to the power m, this to the power n equals b to the power m times n. So again, you show that by induction. And then when you've shown all of that, then you can start playing with those polynomials. I'm sure you've all used those formulas before. Now you're in a position with all the properties of multiplication and addition and exponentiation that we've given. You're in a position to prove that this is in fact correct. So I suggest that you try that out as an exercise. At this point, the algebra you're familiar with has been proved to be correct. So that's cool, right? So I'm not going to go through all of those proofs because I want to get to the next topic. And all of those proofs are a little bit similar. You have to play a little bit to figure out how to do them, but it's just a fun little challenge. So now we are going to get to a slightly different but related topic, which is when we have a set of objects. Remember, a set of objects is just a bunch of objects. There's no order in them. But we might want to generate a list where all the elements are ordered. Okay, so here I've taken a set W, which is words that are often used in English classes for foreign language speakers, EFL, in order to learn different sounds. And obviously, I must have failed that class, but I remember the list. Boat, goat, float, moat, road, rodeo, video. Anyway, that might have been a Brit person who was trying to teach me that. But anyway, here we have 7 words, and we might want to list them. And we might want to list them in different orders. So perhaps we want to list them in alphabetic order. So here I'm labeling it A. Or maybe we want to list them in increasing order of frequency from the most rare of the 7 words to the one that is used the most often. So I've used Google Ngrams, which are really fun things if you just Google Ngrams. It's going to give you graphs of how frequent the use of a word is in the written English language. Google kind of searches all of it and compiles those data points. It's really cool. So on the next slide, I show you graphically what it would mean to generate those lists, and those lists will be generated using functions. Right? So thinking of lists as functions is going to be the key to what we're doing now, so that the process of listing elements is going to be seen as reducing to the concepts of set theory that we've already introduced and established in a very secure way. So in the first case, I have a function from I. I just stands for index. That's the index set that we use. Here I'm using numbers 0, 1, 2, 3, 4, 5, 6. Why? Because there are 7 elements, and I want to say which one is the first, the second, the third, the fourth, etc. Except that since we've defined natural numbers here at starting with 0, we're going to start counting as at 0, not at 1. So we're going to have a 0th element, a first element, a second element, and so on. Those of you who program in Python will be very familiar with this approach because everything starts counting at 0 in Python. So in alphabetic order, the 0th element is goat, the first element is float, the second element is goat, the third element is moat, sorry, anyway, and so on and so forth. Now, if we use the second listing, We again have the same index set. Why? Because the number of elements hasn't changed. We have the same codomain, W, the set of words, but now they will be listed in different orders, and that might be new to you. The least frequent word on that list is rodeo, by quite a margin, actually. Then moat, uh, goat, float, video, boat, and road. Road is the most frequent word on that list by a big margin, actually. It turns out boat and video are quite a bit lower, but very close to each other, and everything else is quite a bit lower. Now, why is moat so unfrequent? I don't know. It's almost like people don't build moats around their houses anymore. Anyway, so you see that we have two lists of objects that are in W, and each of them corresponds to a different function from the index set to the set W itself. So we have two lists, two orderings corresponding to two functions. And this is a really big, deep idea that is going to play a big role. So how many distinct ways of listing the elements of W are there? Well, there are as many as there are distinct functions from that index set to that set of objects that we're trying to order, right? There's going to be a lot of them. 7 to the power 7 is a big number. That's the cardinality of the Cartesian product I cross W. There are fewer functions, but there's still quite a bit of them, okay? So using the functional notation, we can now refer to objects in the set W using f of 0, f of 1, f of 6, right? So here, what is, say, a of 0, boat, a of 3, moat, a of 6, video. What is g of 4, video, right? So you see, this functional notation can now be used to refer to objects of the codomain, the things that we're trying to list. Often, though, we use the subscript notation. So here I've used, instead of F, I've used the first ordering we gave, A, for the alphabetic order, right? So for A0, we're going to take W, small w. Why W? Because, well, the set is called big W, so we think of its elements as small w's, right? So the 0th element of W is the value A0. The first element of W is A1, etc. So here that shouldn't be A6, it should be A parenthesis 6, sorry. So now the word both can be referred to as W0. The word float can be referred to as W1, etc. And if we have listed and indexed all the elements in the set W, then we can redescribe the set W as the set WK, such that K is in the index set, which is a cool notation that you may have encountered before, right? But what is important to notice from our point of view here is that if you see a description like that, it depends on an underlying listing function A, right? The one that maps the indices, yeah, to the elements of the set W. And in that notation, A is not even mentioned, right? But for that subscripting notation to make sense, we have to realize that always implicitly there is a listing function that is presupposed, okay? So that simple procedure gives rise to a much more general thing, which is called an indexed list, right? So the generalization of that concept of indexed list, which is just a function really, right, is what is called a family in set theory. So everything is, it's a big family affair. So then we're going to have a set X, and we're trying to list the elements of the set X. So a family, or an indexed list, if you prefer the term indexed list to the term family, is just a function from an index set to the indexed set, the things that we're trying to list. Right? So that's what I say here. F is the family or the indexed list. I is the index set, and X is the set that we are trying to index. And then any element in the family is going to be an element of the set X. That's the idea. So we are going to refer to the terms in the family as X subscript K precisely when f of K equals X. Right? So that's the idea. So this is how families work. So you perhaps have encountered things like that, and that would be a family of elements of the set X indexed by the set I. Again, here there is a presupposed function, which is the listing function, which isn't mentioned explicitly. But the idea is that each xi in that family is going to be an element of the set X such that f of I equals A, equals that element. So the family of elements of X really is just the range of the function f. This is how all of those concepts of function and indices come together with the concept of a family. Now, some families are so important that we give them a particular name. And this is the case where we index elements using subscripts, and the subscripts are natural numbers, which is a very common case. How often do we use natural numbers as subscripts? Pretty much all the time, right? So families that are indexed with the natural numbers are called sequences. Okay, so if you have a family and the index set is either the set of all natural numbers or a particular natural number, that's called the sequence. Now, if the index set is a particular natural number, then the sequence is finite. And if the index set is omega, the entire set of natural number, then it's an infinite sequence. Now remember, n is a set of natural numbers, right? So 3 is the set that contains 0, 1, and 2. So when we talk about some small I being in n, the index set, we're talking about all the numbers that are smaller than n. So often you're going to see sequences expressed using that notation, using the dot, dot, dot. I call those the dots of laziness. Why? Because, well, it's a finite sequence, so theoretically you could list all the items in order one by one, okay? But it's important to understand that those dots are like, well, what comes in here, right? In a way, you're asking your reader to guess what comes in there. The rigorous way of understanding those is in terms of families where there's a presupposed listing function underneath, which removes all guesses. And then when there's an infinite sequence, there's a dot, dot, dot here and a dot, dot, dot there. That's the standard way in which those are expressed. I call them not just the dots. Well, so here we have the dots of laziness, but here those are the dots of despair because you could never finish listing all the elements. So you're like, dot, 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 right? But again, if we think of this as being an indexed family with an underlying listing function, that is a very perfectly rigorous mathematical object. Okay. So the next thing we're going to do is look at summation of sequences. Now, if you have a particular sequence, sorry for changing slides so quickly, I got confused. So if you have a particular sequence that has a particular length, which is a natural number, then that's easy. You can just say you have 5 items in your sequence. Well, you can just add them one by one. You don't need any new machinery. You don't need anything new for that. But sometimes we want to look at all the sequences that have something in common. Perhaps the terms of the functions of the sequence are given by a function, and we want to come up with a general formula to find the sum of that sequence. In this case, the length of the sequence is going to be a variable that we try to think about. And then, well, we cannot just add them one by one because we don't really know how many objects are in the sequence to begin with. So when that's the case, it's going to be convenient to introduce a new operation that takes as an input a sequence, remember, which is just the range of a family, and maps it onto a number. So it's going to take as an input a sequence of natural numbers and map it to a natural number, which is the sum of the sequence. Right? So it's going to take a sequence of the first n plus 1 elements, and we're going to define it recursively. Whoops, I'm so sorry. So the base case, or the seed value, takes all the elements in a sequence of length 0, right? Which natural numbers are in 0? None, right? So the sum of a sequence of length 0 is 0, right? And then we're going to take the sum of a sequence, but this sequence has for each I in the successor of n. So that means 0, 1, 2, 3, up to n. So there's going to be n plus 1 element. So the sum of a sequence of n plus 1 element is the nth element plus the sum of the sequence that contains all the term except the n plus 1th, which, since we start counting at 0, is xn. Right? So that's a recursive definition for how to take sums of sequences. So let's look at an example of how that would work. So here I'm trying to sum 2 times I for I going from 0 to 5. That is to say, I in 6, or all the numbers less than 6. So that's going to be 0, 2, 4, 8, 10. Right? So we have the sum of that sequence of length 6 is the biggest item, right? So it's 2 times 5, which is 10, plus now the sum of the sequence, but now it's the sequence of length 1 less, of length 5. So then we're going to apply the recursive definition to that term again. And then we get, 2 times 4, which is 8, plus now the sequence of length 4. Now let's add 10 plus 8, that gives us 18, plus the sum of the sequence of length 4. And then you keep going like that. And lo and behold, you get 30, which is, 0 plus 2 plus 4 plus 6 plus 8 plus 10 equals 30. You can do it. Take your time. All right, so please go through all of the lines, and you're going to see how that recursive definition is functioning. Now, mathematicians don't normally use that notation for sums of sequences. They've developed a beautiful notation, which, we're going to introduce now, right? So instead of writing the sum of a sequence that goes up to Sn, whose index set is Sn, so it goes up to n, they use that big sigma, the sum from I equals 0 up to I equals n. So that's the lower limit, that's the upper limit. Why? Because 0 is in the smallest number in the set Sn, and n is the largest number in the set Sn. So then you're going to have x0 plus x1 plus x2 plus blah, 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 dots of laziness, plus xn. So that summation operator, we're just going to, by definition, that's just the summation operator on sequences that I have defined recursively on the previous slide. So if you really like that notation, then you can redefine reformulate the recursive equations, those two equations here, can be reformulated in terms of that sigma operator. So that seed value is one that confuses a lot of people, and that's why I wanted to introduce that notation, because it's a weird thing. What is the summation of all the xi from I equals 0 to n equals 0? Right? So what does it mean to add up 0 elements? That's weird. That's very weird. But if you think of it as adding all the elements in a sequence of length 0, then it makes sense. It should be 0. And then for the sum from I equals 0 up to n plus 1, it's standard here to use n plus 1 instead of Sn, the successor of n. We know they're the same now. Right? So you're going to say it's xn plus 1 plus the sum of length 1 less. Okay, so that's how the recursive definition functions. And then we can use that to prove cool theorems. They're going to be fairly simple for now, since we just have the natural numbers. We don't have subtraction yet. We don't have divisions, right? So there's only so much we can do. But still, we can do something. So here, we're going to show that a sort of generalization of the example that we did before. The sum of the first n plus 1 even number, again starting at 0, is n times n to the n plus 1. So earlier we added all the even numbers up to n equals 5, and we found out that the result was 5 times 6, 30. Oh my God, it was working. Isn't that grand? So we're going to do a proof by induction. Observe that here we have a quantifier for all n followed by a formula. If we remove that quantifier, n becomes a free variable. So that very equation without the quantifier is going to be phi n, the object that we use in order to, the property that we use in order to do an induction. Okay? And as we go along in those proofs, we're both for the base case and for the inductive step, we're going to try to show that the left-hand side equals the right-hand side. And typically, we're going to work on those separately, as you're going to see in the next example. So let's look at it. So in the base case, we just replace n, that's n here, that's n here, and that's n here, by 0. So that gives us summation from 0 to 0. Oh, that's our sum of length 0. And we know that it's equal to 0 by the seed value. Okay, so the sum here is 0. And then for the right-hand side, again, the right-hand side is n times n plus 1. We get 0 plus 1 equals 0, which is, of course, 0. So that means that the left-hand side and the right-hand side are equal when you replace n by 0. Easy. Now, the inductive step. You pick an arbitrary object, and you suppose that the equation is true for n. Okay? And then we try to show that the equation is also true if we replace n by the successor of n, or as we write in those proofs, n plus 1. So you see, I took the exact same equation, but for each of the 3 occurrences of n, I've replaced them by n plus 1. So now I'm going to work on my left-hand side and my right-hand side separately, trying to show that they are equal with each other. So then I start with my summation from I equals 0 to n plus 1 of that thing. So I use my recursive definition, right? My first term is 2 to the n plus 1 because remember it's xi, so here my terms are defined using the multiplication 2 times I, so 2 times n plus 1, plus the summation, but now it's up to n, not up to n plus 1. Okay. Now remember, my inductive hypothesis is that the equation holds true for n, right? So this element here is known to be equals to n times n plus 1. So I replace it, substitution of identicals. And now I have that here. And now earlier on, we've proved everything about multiplication and addition, which is needed to simplify that expression. And it gives me n squared plus 3n plus 2. Now let's work on the right-hand side. Again, it's just basic algebra based on the properties that we have proved. First, n plus 1 is n plus 2. And then we use distributivity, and that gives us n squared plus 3n plus 2. So we simplify again, and we obtain the same result. So the left-hand side for n plus 1 equals the right-hand side for n plus 1, which shows that phi of n plus 1 is true. So phi n implies phi n plus 1. That completes the inductive step. And so the result follows by induction. So that's a beautiful proof, isn't it? So there's a couple exercises like that in notes, and I encourage you to try to do them. So that was it for this lecture. I hope you've enjoyed it and that you will have fun proving tons of things by induction, especially about things that have been defined recursively and things that are listed using this concept of sequence. All right. So on that note, cheerio, have fun.